Hi, I'm Henry Segerman. In a previous video, I talked about these 3D printed expanding gadgets. They use rack and pinion mechanisms to transfer force around so that everything expands at the same time. These all expand in 2 dimensions, getting bigger on the table, but not increasing in height above the table. So the obvious question is, can we make a mechanism that expands into all 3 dimensions? Well, this is where we're heading, a design that expands in all 3 dimensions. The story of how I got there involves mechanical engineering and 3D printing, of course, but also lots of symmetry and even a bit of crystallography and chemistry. First, let's take a look at how the 2-dimensional grids work. There are junctions that each have a gear inside, and the junctions are connected to each other by pairs of racks. The racks and gears are a bit difficult to see in this design, so I made a demo version to show what's going on more clearly. Here's the base for one of the junctions. 4 racks slide into the base. Then we put in a gear that meshes with the 4 racks. When any of the racks moves, it turns the gear, which moves the other racks. Now let's take another copy of the junction and put it to the side of the first one. Next, we connect the end of this rack to this base with a bolt, and connect the end of this rack to this base with a bolt. Now, what's going to happen if we move this rack? It will rotate this gear, which pulls this rack in, which also pulls its base in. That pushes this rack against the gear, which rotates the gear, which also moves its racks. Okay, let's see it. So the force transfers along the mechanism from one junction to the next, through the pairs of racks connecting neighboring junctions together. And we could do the same thing with junctions connected to these racks, and we build out the 2-dimensional grid. This is all that's happening in the big grid designs. The only difference with this demo mechanism is that I move things around so you can see everything that's going on from this camera angle. So, how do we make this into some sort of 3-dimensional grid? At each junction, the gear and the 4 racks lie in a plane. So somehow we need to break out of that plane. You might imagine twisting the racks around the gear. I have some plans to do that, but that's a story for another video. For now, I want to explore what happens if we keep the racks in the plane of the gear, but rotate neighboring junctions, like this, so that they don't all lie in the same plane. The mechanism still works exactly the same as before. The only thing that has changed is that the 2 gears used to be in the same plane, but now their planes are rotated relative to each other. But how does this pattern propagate outwards? When everything was in one plane, we made a square grid. Do we still get some kind of grid now? What's the large-scale pattern? This all depends on what the angle between neighboring junctions is. There are lots of options, but your first thought might be to try a right angle. Let's visualize what a right angle pattern would look like. Here I'm using this building system called Zoom Tool that lets you build all kinds of mathematically interesting shapes. I'm only going to use these blue struts, which come out of the zone balls at right angles to each other, but there are other colors of strut that come out at other angles for building other structures. I'll use the zone balls to represent the junctions, and blue struts for the pairs of racks going between the junctions. Actually, here's a quick aside. How do you think they make these zone balls? They're injection molded. You squirt molten plastic into a metal mold, but how does the mold release the ball once the plastic has solidified? It's not like you could just crack the mold into 2 halves and pull them off. Parts of the mold have to go into all of the holes. And what about the cavity in the middle? How could the bit of the mold that makes the cavity possibly get out? Well, let's leave that as a mystery. For now, here's a zone ball and 4 struts representing a junction with 4 racks coming out of it in a plane. And the next junction has its 4 racks also in a plane, but angled at 90 degrees. If we keep building outwards in this pattern, we discover that it links up with itself here, making a kind of right-angled hexagon. This is good for expanding mechanisms. Relatively short closed loops help with transferring the forces around. In the 2-dimensional square grid, we have loops of length 4, and 6 is not much longer. And of course, it's good that the pattern joins up at all. If the angles were slightly off of 90 degrees, then the pattern would not quite match up. It would instead crash into itself, which obviously wouldn't work. Although maybe it shouldn't be surprising that the 90-degree pattern does match up nicely. This right-angled hexagon is made up of the edges of a cube. If you stack cubes together, you get the nice, regular Minecraft tiling of 3D space, and our pattern will live on the edges of that tiling. If we continue building the pattern outwards, we end up making this larger cube shape, made out of 8 of the smaller cubes. And now the whole pattern is made by stacking those larger cubes together. Let's actually see what the whole infinite pattern looks like. You might have already guessed that this structure shows up in chemistry as the atomic structure of a crystal. This is the arrangement of niobium and oxygen atoms in niobium monoxide. According to Wikipedia, niobium monoxide is a grey solid, which sounds pretty boring, but more interestingly, it's also a superconductor. Niobium monoxide has the chemical formula NBO, so this structure is called the NBO network. Okay, I lied. What you're seeing isn't actually the whole infinite pattern, but getting this video to loop so that it looks like we're endlessly traveling through the NBO network was a fun side quest. This was the same kind of camera motion control project as my real-life fractal zoom videos. The camera moves forward on a slider, going from one view of the object to an almost identical view, so we can fade from one view to the other and the video loops. In the fractal zoom, going from one view to the other corresponds to scaling the 3D print. But since the print is a fractal, we can move towards it instead of scaling. Here, going from one view to the other corresponds to moving through the NBO network. So the camera has to move quite far into the zoom tool structure without crashing into it. I use this probe lens to do it. It can get far enough into the structure that we see the same pattern again, so we can fade from one view to the other and make the loop. I use this grid on my lights, which reduces how much the light spreads out. So in the view from the camera, we can't see that far into the distance, which reduces the amount of stuff popping in as we go around the loop. And I move the light with the camera so that the lighting would match between the start and the end of the loop. While I had the zoom tool structure set up, I got some other shots moving into it. There are some very pretty views that show the different symmetries, but I didn't bother trying to get things lined up well enough to make them loop. Alright then, side quest completed. So this is the pattern we want to recreate with racks and gears. But there are more things that need to be worked out. For example, which way does the gear rotate in each junction when we are collapsing or expanding the mechanism? Can we set it up so that they all rotate the same way? What would it even mean to rotate the same way when the junctions are in all of these different orientations? And here's another thing. At each junction, the 4 racks are on 2 different layers. Which racks go on which layer? In other words, the expanding rack mechanism has to break a lot of the symmetries of the NBO network. I did want to keep as much symmetry as possible though, both to reduce the number of different parts I had to design and to make the thing simpler to build. Let's come back to the large-scale symmetry later. For now, here's the design I went with for the junctions. It looks a bit different to the demo junctions from before. The final design has more symmetry than the demo version. Both designs have this 180-degree rotation symmetry, but the final design has another symmetry that swaps the top and the bottom halves. But this other symmetry is not a rotation, and it's not a reflection. Let me try to explain. Here are 2 identical copies of the junction. If I turn this one over, the other side is not the same as what we started with. If you look at the racks on this one, they kind of slope upwards as you look to the right, while on the original they slope downwards. This is in fact a mirror image of what we started with, so that extra symmetry is not a rotation, but it isn't just a reflection either. If you look around the junction from all directions, there's just no plane of mirror symmetry. So there's no simpler way to look at it. This other symmetry is a combination of a rotation and a reflection. Anytime I've got some kind of symmetry question, the book I reach for is The Symmetries of Things by John Conway, Heidi Bergiel, and Chaim Goodman Strauss. And there's a just-released, greatly expanded, much abridged follow-up, The Magic Theorem. These books give a really nice notation to talk about symmetric objects. In that notation, the symmetry of the junction is 2x. The 2 means that there's an axis you can look along, which has twofold or 180-degree rotational symmetry. The x means that you can rotate it from one view to a reflection of that view without going through a view that has mirror symmetry. Here the book points out that a baseball has the same kind of symmetry if you pay attention to the stitching along the seam. It's got a twofold rotation axis here, and if you flip it over this way, it will look almost the same except that the seams point in the wrong direction. So you get to a reflection of the original view. And yet, just like the junction, the baseball does not have a plane of mirror symmetry itself. I made these 3D prints to illustrate the different kinds of spherical symmetries for my book, Visualizing Mathematics with 3D Printing. Here's a 3D print that has a similar kind of symmetry to our junction, except that this one has symmetry type 8x instead of 2x. It's got an axis with 8-fold rotational symmetry here, that's the 8, and we get an x because you can rotate from this view to this one, which is a reflection of where we started, even though again there are no planes of mirror symmetry. So the symmetry of the junction is 2x. This affects how we can 3D print and assemble the junction. If a gear and a rack are both horizontal as they're printed, then they contact each other along layer lines of the printing. If they were printed in different orientations, then they would roll over each other's layer lines, and the mechanism would not run as smoothly. So we want to print the gears and the racks horizontally, and we also want the print orientations to match when we've got axles contacting the inside of gears and these rails that slide in grooves on the racks. A single junction then has parts needing to be printed in 1, 2, 3, 4, 5, 6 different orientations. These parts all need to be rigidly connected together, ideally without using too much hardware. An extra bolt here and there, like I used in the demo junctions from before, might not seem that big a deal, but this junction design is going to get copied many times to make a bigger structure, so weight becomes an issue. So I'm pretty happy with this design, in which a single bolt connects all the parts in a junction together and holds the gear in place on its axle. There are these little cap parts that the nut and bolt sit in that hold the racks in place on the base. They can be fiddly to put in. You kind of need to angle the two racks up and then press them into place with the cap. Okay, so let's build one of those right-angled hexagons. So yeah, this seems to work very well. I was a little worried before I built this that somehow going around all these weird corners would cause a problem, but it seems to work fine. We only need racks to connect together pairs of junctions, so I don't need these racks pointing away from the hexagon. So let's remove them. For these junctions that don't have racks going off in all 4 directions, I've got a version of the cap part that also fills in for one of the 2 racks on its side of the junction. We can also add extra racks meshing with the gears that don't connect to bases, like this. I think this makes it look cooler, it makes the expansion visually bigger. One of the advantages of having lots of symmetry is that it makes the assembly rules easier to remember. There are just fewer rules to think about. So here are the rules for this design. First, every junction looks the same, apart from when we remove the rack going off in some direction, like we did for the hexagon. Second, when 2 junctions connect together, the grooves on both racks have to fit onto rails on the 2 bases. And that's it. There's only one way to put 2 junctions together so that both racks fit onto rails. The 2 racks have to have the same handedness, and they have to be the right way round. So there's only one way to build everything outwards. The only choice is how much to build and in what shape. Well, okay, next let's do a cube. This is made from 8 overlapping hexagons, 1 for each corner of the cube. By the way, I'm using red, orange, and yellow for the colors of the junctions in the 3 different planes, but the colors don't mean anything else. All of the junctions are exactly the same as each other apart from the color. This time I didn't add on the outside racks, which reduces how much it looks like it expands, although if we just build something bigger, the boundary of the shape won't matter so much. Okay, now we're getting somewhere. This is a nice compact Tetris piece that will fit in my luggage, but that I can easily expand out to make a much bigger Tetris piece. With this much of the structure built out, I can show you why the racks are the length that they are. It would be great if I could make them longer so that the expansion factor would be bigger. But here's the problem. This rack is at the same height as this one, and when we collapse the structure down, this one pokes straight into the side of the other one. I don't think there's any way to tweak things a little bit to get them to avoid each other. The symmetry just doesn't allow it. So this is as long as the racks can get if I want it to be able to collapse down this far. Still, we get a pretty good expansion factor with these racks, just over a factor of 2. Alright, so the Tetris piece is bigger than the first cube I made in 2 directions, but since we're doing expanding racks in 3 dimensions, we obviously have to make a structure that is big in all 3 directions. So let's make a 2x2x2 cube. So let's see. Seems to work pretty well. It's got pretty heavy, just the amount of stuff here. So Lifting it from there requires a lot of force just because I'm lifting half of it up like this. Somehow it's easier to do from up here. But yeah. Here are some motion control shots I took to show the movement a bit more smoothly than I can do by hand. Here I'm using the probe lens again so we can see inside the structure. Right, you can see we actually get a factor of about 2 in the collapse. Here's one of the original cubes, and it's about the same size as this 2x2x2 chunk of cubes here. So let's see. Now that we've got a 2x2x2 built out, I can explain another interesting feature of the NBO network. So again, this is the 2x2x2 cube. It's made of 8 copies of this. I'm actually going to use the zone tool instead, just because it's a little easier to see what's going on. So again, this is one of the cubes, and here are 8 of them stacked together. And I've got my Rubik's Cube to indicate where those cubes are. And so, well, of course, you've got one of the cubes here in the top corner of this structure here, and there's 7 more. Now, what I want to point out is that there's a whole other set of cubes here which are kind of dual to the first set of cubes. So there's one here. Here there's sort of half of this cube is built out in the zone tool structure here, and then next door to that cube is this one here. This maybe has only a quarter of the cube built out in zone tool, and then there's a central one right in here, which again is sort of offset from the original 8 cubes that we thought we were building. But yeah, so there's this whole other sort of dual set of cubes sitting inside of this structure, and this other set of cubes is going to help us understand the large-scale symmetry of the pattern later on. This 2x2x2 cube is also going to let us see how the pattern tiles out into space. So let's pay attention to this junction here, and I've got a copy of it here in the same orientation. So you can see the 2 horizontal racks here, and it sort of slopes upwards. So if I go back 2 cubes, then we should be looking at this one here. This junction here is again in the same orientation. And that's not true if I just go back 1 cube. So going from here to here, this one is not in the same orientation. I have to rotate it like this to get it to match up. So what does that mean? It means that if I take 2 steps, then I see exactly the same thing, which means that I could take this entire structure, shift it back 2 cubes, and it would match up with itself and it would tile. And that's the same in the other 2 directions as well. If I go this way, it's the same. If I go this way, it's the same. So as long as I take 2 steps every time, I see exactly the same thing, and I can tile out space with the pattern. This book, The Magic Theorem, is greatly expanded over the previous The Symmetries of Things, in that it has many more examples and details about the symmetries of 2-dimensional things, planar patterns, patterns on the surface of a sphere, and so on. It's also much abridged in that it doesn't go into the symmetries of higher dimensional things, like the NBO network. So for that, let's go to The Symmetries of Things, chapter 22, on the 35 prime space groups. Let's not get too far into the details because there's a lot going on here, and I certainly don't understand all of it. But the short version is that these kinds of symmetries of repeating 3-dimensional patterns are governed by these 2 checkerboard patterns of cubes, red checkerboarding with green and yellow checkerboarding with blue. I asked Chaim, this Chaim, about the symmetries of the NBO network and my expanding racks version. And we worked out that the NBO network has symmetry type 802, which Conway names the doubled octat group. The expanding racks mechanism breaks some of those symmetries. It has symmetry type 4++, the bipositive hybrid tetrad group, apparently. You can see the relations between the different symmetry types on this diagram. As we go down these curves, we're moving to subgroups, so we break some of the symmetries as we move from 802 down to 4++. By the way, this zone tool structure doesn't quite have the same symmetries as the NBO network itself if you pay attention to the geometry of the zone balls and the struts. You can rotate the NBO network around one of its junctions by 90 degrees and it looks the same. But that's not true if you look closely at the zone balls and the struts. So this zone tool version of the NBO network actually has yet another symmetry type. Chaim and I think it is the null doubled tetrad group 402. One of the things I found most confusing about the symmetries of this design was what is the transformation that takes you from, say, this orange junction to a neighboring junction, say this red one. So here's a copy of this orange junction. You can see that this rack is in exactly the same orientation as this one. Of course, I've removed these two here from this one because they go off the side of the cube. So obviously I have to move, I have to translate over here, but I also have to rotate to get it to match up with the red. So I move forward and I rotate like this, and you can see the orange is in exactly the same orientation as the red. And so this was like a right-handed screw motion. As I move forward, it's like I'm tightening a screw with a screwdriver in the usual way you would do so. So this is a right-handed screw motion. Now what if I want to go from this orange one to this yellow one? Again, I have to translate, but now I do this rotation to get these two to match up to be the same. And this is a left-handed screw motion. So why is it that sometimes I have to do a right-handed screw motion and sometimes I have to do a left-handed screw motion? Why isn't the thing to do to just always turn the same direction? There's a really nice way to think about this that Chaim and I discovered once we knew that the symmetry type is 4++. We looked up other structures that have the same symmetry and found this, the mu-cube octahedron. This is a surface in space made out of squares and hexagons. You can also think of the mu-cube octahedron as being part of the tiling of space by truncated octahedra. An ordinary 8-sided die is in the shape of an octahedron. If you cut off all of its corners, like this, then you get a truncated octahedron. And truncated octahedra can tile together to fill space. If you take the two-dimensional faces of that tiling and delete some of the hexagons, you get the mu-cube octahedron. In the tiling by truncated octahedra, every edge meets 3 polygons, 2 hexagons, and a square. Every edge loses 1 hexagon, so it ends up with only 2 polygons next to it. That means that we end up with a polygonal surface. You could even smooth it out a bit, and you get this minimal surface, which is called the D surface. The D stands for diamond. The surface cuts space into 2 sides, each of which contains a copy of the molecular structure of diamond, which is where the name comes from. So if the surface has 2 sides to it, shouldn't the mechanism also have 2 sides? But what could that mean? Maybe pause the video for a second if you want to think about it. The answer is very satisfying. Okay, the junctions and their gears correspond to squares in the mu-cube octahedron. As the mechanism collapses or expands, the gears rotate. The 2 sides of the mu-cube octahedron tell you which way the gears rotate. Let's see how this works. Suppose that you're inside of this cube looking out at one of the junctions, say this one. Now, which way is the gear in this junction going to rotate as we collapse the mechanism down? It's a little difficult to see because the gear is kind of covered up, but you can tell by the positions and the movements of the racks that this gear is rotating anti-clockwise as we collapse the structure down. Let's take a look at some of the other junctions around here. So this one here, again, as we collapse down, the gear rotates anti-clockwise. Maybe let's look at one more. As we collapse down, the gear rotates anti-clockwise. So you could say that this is an anti-clockwise rotating cube. Now, what's going to happen if you look from the perspective of the next door cube over here? So let's look at this junction. And now what's going to happen, of course, is that the gear rotates clockwise as we collapse down. Of course, it must rotate the opposite way from when we were looking from this side. It's the same gear, you're just looking at it from the back side. If you look at a clock from behind, the hands of that clock are going to rotate in the anti-clockwise direction. So next to this anti-clockwise cube is going to be a clockwise cube. In fact, all of its neighbors are going to be clockwise rotating cubes. So that means that in a grid of cubes, we get a checkerboard pattern of cubes where the gears rotate clockwise or anti-clockwise. But there are also all of the cubes of the dual grid, and they also have a checkerboard pattern. These 2 checkerboard patterns are the red, green, yellow, and blue balls from the book. The mu-cube octahedron separates the red and yellow balls from the green and blue ones. So it separates the clockwise rotating sides of the junctions from the anti-clockwise rotating sides in my geared NBO network. So why, when we move from one junction to the next, do we sometimes rotate to the left and sometimes rotate to the right? Well, you have to rotate to keep the clockwise rotating side of the junction on the correct side of the mu cube octahedron. So sometimes that means rotating left and sometimes that means rotating right. Isn't that cool? If you'd like to print some of this expanding NBO network design for yourself, I've put a link to the files in the description. And one more thing, I finally got around to setting up a Patreon at patreon.com/henrysegerman. There are some posts up already with some behind-the-scenes details about the Alpha Omega D24 video, and some work in progress details for the follow-up to this video on an expanding racks design based on the Triamond lattice. I've also just put up a post with some extra details about this video. In the future, I'll plan to post early versions of videos or other updates of things I'm working on, so if you'd like to support my work or just see more about what I'm doing, please consider joining. Alright, that's it. Thanks for watching.